Good morning everyone. Today we are going to start with the course on systems engineering, and today is the first lecture. It's on the introduction to systems engineering, and I am Dr. Deepa Philip. I am from IIT Kanpur and I am a faculty in the industrial management engineering department and as well as the design program, and I am a systems engineer by trade. Before we get into the details of systems engineering, let us talk about how the dynamics of this course will work. At this point, this course will be a combination of multiple 30-minute lectures which will be delivered to you, which you will listen, are expected to listen, and then followed by weekly assignments which the student will use materials available and provided as part of the course to read and complete the assignments. There will be few real-time case studies given which the student is supposed to read and understand and then answer the questions that follows the case studies, and also there are some will be weekly assigned readings, which also it's the responsibility of the student. So it is a mutual course in which both the participation from the students are also equally important. The assignments and the submissions worth a total of 30 points or 30% of the total points, and the final examination will be worth 70% of the total points, and the duration of the course is about 7 to 8 weeks. The basics of the system, let's talk about the basics of the system as such, or what is the simplest things about a system. There are many definitions available to the system, but for the purpose of this course, we will look system as a composite of people, products and processes. So when you talk about people, this part, the first part is all about the manpower, which can mostly involves the human resources, which sometimes people call as HR, plus the users of the system, and as well as the people who are basically the beneficiaries of it. So these people, everybody, all these things put together gives the component of the people. The products are really tangible things. Let's put it tangible things for the time being. We will elaborate this later. And processes is typically the set of sequenced activities. These sequenced activities will result in creating a product or a subassembly of the product. So a system is a composite. Composite means it's a conglomeration or a mix of all these things. And another aspect of the system is that these components are also interact with each other. Interaction means the people will interact with the machines, the subassemblies, the products, the components, the processes. So everybody working together from in a unison to really create what we call as a final product. In this case, we are not talking too much about the services components. We are mostly focused on product side itself. But these interactions actually create complexity, because when there is a man and a machine interaction, there is an interface, and that interface usually creates additional complexities. There is a stated common need or an objective. That means the system as a whole has one common objective, which is stated. Stated means it is known, well known to everyone. So this objective is stated, and everybody, all components work towards satisfying this stated goal or objective or need. Then other aspect that actually comes out of this is a term called life cycle. People use life cycle in the sense that it is the life cycle of a product or a system or a human being or something like that. Here what we talk about life cycle is that the end to end, from design to production to usage to redesign. So it is a cycle where you start from the design, then you move to the production, from production you move to the usage, from usage to the redesign, and the cycle continues. So the life cycle of a product is actually a system is a mechanism in which the product goes through multiple iterations and improvements. So, all these are aspects, that terms that we will come through in the discussion of this course. In a systems engineering, there are two major disciplines when we talk about this. The first one is actually called as a technical domain. The technical domain particularly deals with the technical know-how of the product development. So, let us say that you are working on development of aircraft. So, an aircraft typically has 5, you can think about it in 5 parts. One is an airframe, then there is a propulsion, then there is a control, which is an autopilot and other kind of things. Then usually there is a payload, or whatever you call as the human beings that we are being carried, and as well as the last part is the communication. So, the technical know-how here, this might require a mechanical engineering, this might require an aerospace engineering, this might be knowledge in mechanical plus electrical engineering, this might be an electrical engineering specialty, this might also require computer science engineering, this would require what you call as the ergonomics people, human factors and stuff like that. So, this is the technical aspect of systems engineering. Multiple diverse technical know-how is necessary to realize a product. But another aspect of it is all of these things that we just wrote here need to be managed together to realize the common stated goal. This part is the aspect of the systems engineering and management. How do the diverse aspects, technical aspects of a system gets managed towards realizing the stated goal. So, strictly speaking, systems engineering is a very strong interdisciplinary field, which is a field of engineering and engineering management. So, initially let us talk about the definitions, how systems engineering evolved as a discipline. So, you can see that it started in 1974. This is the military definition, MIL standard 499A. It is no longer it is depreciated. People say that it is an outdated definition, but still this is where systems engineering began. So, the origins can be traced to the defense or military background, and the initial definition reads something like this: a logical sequence of activities and decisions that transform an operation need into a description of system performance parameters and a preferred system configuration. So, initially systems engineering SC was targeted more towards developing a parameters of the system, the performance parameters of the system plus the configuration of the system. So, this is where the systems engineering began. What are the specific parameters of a system, which or what are the logical sequence of activities and decisions that can transform the need of this operational need. This is by the customer. Whatever is the operational need of the customer, how can it be realized with a set of system performance parameters and a preferred configuration. So, initially systems engineering was limited to this in 1974, and this is where the humble origins of it happened. From there, let us move to the next definition, which is something called as a revised definition. So, the SE, by the way, this acronym stands for systems engineering, and the revised definition states that like something like this: an interdisciplinary, this is the first word, collaborative approach that derives, evolves and verifies a life cycle balanced system solution which satisfies customer expectation and meets public acceptability. It was in the IEEE P122, this is September 1994 definition. As you can see, here you can see that the definition has evolved much more significantly. The concept of interdisciplinarity, where multiple technical fields of engineering to be collaborated together. So, the collaboration concept, collaborative approach, they are working in unison. This concept started coming in. That derives, evolves and verifies. So, derives, this is the point in which you are basically defining the parameters, and then evolves is how are you realizing the parameters, and verifies, this is where the you can think about it as a check or a quality control, something like that, okay, of the life cycle based system. We are not talking about a product, we are talking about a system solution that satisfies the customer expectation. So, you take the customer expectations, and from there you derive the parameters, then from there you evolve the system design, from there you verify that the evolution evolved system design meets the defining parameters of the customer expectation. And this concept of public acceptability was also included at that time. Public acceptability to a large extent is the classic example of this is the state of aircraft called Concorde, which was designed as a supersonic commercial aircraft. I would recommend you guys to read about this. This aircraft was it could travel from London to New York in like 3-4 hours, between 3 and 4 hours. So, it has reduced the travel time into half pretty much compared to the normal travel time. But Concorde was stopped. One of the main reason was because of the noise levels at landing and takeoff, which was unacceptable. So, this was the reason this product was not being supported by the general public, and the public acceptability was not there. Hence, Concorde services has to be shut down. So, read about this Concorde aircraft of both British Airways and French systems as well. So, the public acceptability was an important aspect in the definition when the systems engineering definition was revised. Then the definition got refined further. It is in the December 1994, EIA stands for the Electronic Association. So, what they ended up doing is that the IS 632 standard, the systems engineering definition was further refined to be again an interdisciplinary approach. So, the interdisciplinarity concept remained, that encompasses that entire technical effort. It just did not talk about just starting from the deriving the specification from the customer needs. It talked about the entire technical effort related to the system design. So, this entire technical effort and evolution or evolves into and verifies an integrated and life cycle balanced system people. So, here the concepts, the major aspects of the system, the people, the products and the process solutions that satisfy the customer needs. So, these three aspects of the system, the people, the products and the processes, were spelled out in this definition, and the customer needs, again you can see that it stays. One of the questions that people actually ask here is, what happened to the public acceptability? Did it got dropped? Well, public acceptability is still there. The aspect is here, the life cycle balanced set of system. This incorporates the public acceptability. So, these definitions, when you see that slowly evolved over time, and as the systems engineering spread its wings and the evolution of this discipline into a umbrella system that actually guides the development of a complex system. Now, with this we move to the what you call as the current systems engineering definition. To a large extent, the Kosikov and all in 2011 has provided this definition, which is a much more simpler definition. What it is, it's the management and guidance, and manage and guide the development of complex engineered systems over their life cycle. So, you can see that the definition is now to complex engineering systems. To a large extent, we are not involving the life systems or ecological systems. In this case, we are talking about engineering systems or man-made systems, and the life cycle of the systems is still an important aspect. So, throughout the entire life cycle, and manage and guide is supposed to have all the aspects that we talked about: the people, the product and the processes that relates to the development. So, all of these results in the development of the complex system. So, it is a much simpler, shorter definition, but lot of things are hidden together into this. So, the essence remains the same, it does not change too much, but the definitions, as you can see, it increased the scope of the systems engineering. So, some of the explanations to recap on what we just discussed so far. So, system complexity, one of the terms that we talk about, complex systems, design of complex systems. So, what is a complex system in a simple way? So, if you talk about a washing machine at home, that is not a complex system, because it is household systems, a refrigerator, many people do not consider it as a complex system anymore. But if you talk about a aircraft, you talk about a communication system, you talk about a missile system or integrated command and control systems, or you talk about a transportation system, all of these kind of things, the complexity where you have multiple diverse components interacting together. So, the diversity of the components to a large extent determines the complexity of the system, and many of these components have intricate relationships with each other. When you have diverse components interacting with each other, the relationship sometimes becomes intricate. Like for example, in an aircraft, the control system might tell the deflection of a control surface to be 2 degrees or 3 degrees up, down, something like that. So, plus 2 degrees or minus 3 degrees. But what does that translate to the change in the behavior of the aircraft, or how does the aerodynamic forces actually gets translated? That is something that is a job of an aerospace engineer. He might have given this, okay, if you deflect it by 2 degrees plus 2 degrees, then this is what will happen to the aircraft. If you deflect the elevator minus 2 degrees, then this is what is going to happen. He has already provided that information, but that intricate relationship gets translated to a computer program, which actually ensures that the control surfaces get deflected by that exact degrees. So, that is an example of a complexity, and this deflection to a large extent depends upon the speed. So, if it is flying faster, you might not require that much of deflection to generate the same amount of force. So, as the operational environment changes, this intricate relationships, so this to a large extent depends on operational environment. Then also other part is a common objective. All these systems, all these components should have a common objective, which is a significant function of the system. So, the significant function of the system or an aircraft system is to fly people from place A to place B safely, or transport cargo from place A to place B, or deliver an ammunition at a precise location as quickly as possible. The significant function is that, and how it achieves that significant function, the common objective, is the important aspect of this aspect of the systems engineering. As we said, it is an engineered systems, so we exclude all living things and ecosystems. So, we are not studying about how the plants and the flora, fauna, or a forest as an ecological system. We are not worried about that. We are more worried about man-made human systems. Some of the examples, see, in this case, this course, we are typically going to follow on a system-centric approach instead of a domain-centric approach. So, we are not going to look at system from an electrical engineering standpoint, or a mechanical engineering standpoint, or an aerospace engineering standpoint. Instead, we would actually look at it as an aircraft, or a transportation system, or a communication system, and the components of it, and then how different domains interact in that system to realize their successful common stated goal. Some of the examples, as I mentioned before, aerospace systems, complex structures, then chip design, which is in fact a complex system, IT systems, IT enabled systems, actually defense systems, healthcare is another complex example, complex system design examples. So, you can see that systems engineering is not just limited to one field of engineering, it is actually spread all across the world, all across the technical domains of different engineering disciplines. So, let us talk about the systems engineering management, because we said the current definition says manage and guide the development of a complex system. So, what is the management component of this? So, this actually the credit goes to the engineering, the systems engineering fundamentals by the Defense University DAU, and this is a January 2001 document. It actually says the systems engineering management aspect has 3 major activities. Okay. And the first one is called the development phasing. We will go through each one of them in the subsequent lectures following this lecture. We will discuss the details of it, and we will go through the intricate details of each one of them, what does this actually means. So, the number one is the development phasing, number two is the systems engineering process, and number three is the life cycle integration. So, how do these three behave together? So, the first one you can think about is the development phasing, followed by what we call as a systems engineering process, which actually overlaps with the development phasing. On the top of this, then we have the life cycle integration that interacts with all the three, and from there we get what we call as a systems engineering management. So, this red bubble where everything comes together, you can think about that's a place where the systems engineering management finds its aspect together. So, the development phasing to a large extent is the first phase of systems engineering, and this is where we specifically freeze the objectives of the system. What happens here is we derive what are the major objectives, what are the things that the systems need to achieve as part of this, what are the major functionalities, or what are the major, not functionalities, the right way to say it is like let us say for example, if you talk to the people in Boeing and ask them what was your the development phasing when you developed the Dreamliner 787, what was the major aspects of it. So, it was turned out to be like a very successful long range carrier which was minimal noise and vibration levels and as well as extremely fuel efficient. So, that important aspects, important stated goals and objectives actually comes out as a result of this development phasings. Once that comes in, second step comes is the systems engineering process. So, once you have the objectives, then from there you need to derive something called as specifications, the system specifications. What will be, so when you say that okay, this has to be a fuel efficient aircraft, what is fuel efficiency? How many miles per nautical miles per gallon of aviation turbine fuel, or it should be the most silent aircraft. So, then what is the noise level? Specify the noise level, how many decibels is acceptable. They might also said that it should be most of the aircraft components should be made of composites. What percentage? 10%, 20%, 30%, 50%. So, the objectives that are loosely stated in English gets translated to quantitative, measurable and verifiable facts. That is the major aspects of systems engineering process, the second stage. There is one more thing that actually happens out of this systems engineering process. The teams that will realize different aspects of the product development or the complex system development that we talk about also gets formed as part of this procedure. The teams, in a sense, the teams, like somebody will be, for example, if you take the Dreamliner 787 case, there is a team that will focus on developing the engine which is fuel efficient, minimal vibration, but also able to give sufficient speed to the aircraft. So, then they will exclusively work with some set of people, their aim is to basically realize that. Then there will be another team who is a materials team whose job is to actually how to integrate different composite materials with the typically accepted body of an aircraft which is made out of an alloy called duralumin. So, that they will be focusing on that. So, there are different type of teams who will actually focus on different aspects of the system, and the systems engineering, a systems engineer's job is to actually manage and actually supervise or in a say guide that teams in realizing the stated objectives of the system. So, the aim is to realize these. Okay. Once this is done, once the specifications and the teams are frozen out, then comes the life cycle integration, because one of the things is at the end of the day, whatever product or whatever system you design, if the customer does not like it, it is not going to fly. So, this is where the life cycle integration is where the customer is integrated into the system. Means the customer decides whether this is the right thing to do or this is the stuff that he or she needs to change, or what are the other evolutions that are need to be part of the stuff. That all comes as part of this. So, quickly we will talk about how the systems engineering and the traditional engineering differs, and what are the similarities. The systems engineering always focus on the whole system. It looks at the system internally, which is the people, processes and the products, sub-assemblies, and it also looks at it externally. So, the internal aspects is the people, processes and products or sub-assemblies, whatever you want to call it, whereas the externally, that is the environment. We talk about the public acceptability. This concept comes out of here. So, both the environment in which the system operates and the internal aspects of the system, both are looked into. So, that results in the total operations. These two together gives you the total operations of the system. So, it is not just an engineering design. Please remember this. This is one of the most important aspects. It is not just an engineering design, but it also has external factors on it. So, the customer needs, the operating environment, interfacing systems, logistics requirement, what type of things are required to transport it from place A to place B. Do we have the sufficient personnel to operate the system? Are there enough capabilities, or do we need to provide additional trainings or tradings? All these kind of things are part of the systems design. Okay. You have to make qualitative and quantitative judgments. Qualitative means you cannot have everything measured by a number. Like for example, what should we paint the aircraft? What should be the painting scheme of this? You cannot say that, okay, this much percentage white or something like that. You might say, okay, it could be a mix of these because it gives you a different appearance. You might want to say that, okay, you might want to paint it with a paint that might reduce the skin friction drag, so that the noise and vibration levels are reduced. So, how much you can reduce, you can probably quantify, but then the aesthetic appeal might be a qualitative judgment. So, the systems engineering also involves both qualitative and quantitative judgment, and all of these things are integrated into the final design of the system. Together with that, so this is the difference between a systems engineering approach and the traditional engineering. And who are systems engineers? Their major responsibilities involve lead the formative stage of the system development, the first phase, then where you actually evolve the functional design of the system, where you comes to the specifications and as well as the team. So, here is the objectives, here is the specs plus teams, and then here is the life cycle. So, they bridge the traditional engineering discipline. So, systems engineers are to a large extent jack of all trade, master of none kind of a thing, where their major aim is to engineer complex systems, where it cannot be engineered. Such a complex system has so many diverse technological skills necessary, so that they cannot be engineered independently. So, summarizing today's lecture, what we talked about it is the systems engineering is all about setting objectives for the system development, then guiding the execution. Once the execution is over, you evaluate the results against the customer specifications or customer needs and prescribing corrective actions. All of these will ensure with one goal: maintain the systems development in course, keep the systems development in track, ensure that the system development process in such a way that the stated common goal, this is the most important aspect of systems engineering. What are we supposed to achieve? Is it getting achieved? Is it getting achieved? This question is something that keeps the systems engineer on track, and he ensures that the rest of the teams are also kept in track. Thank you for listening to the first lecture. I hope that this lecture will be supported with the assigned readings and as well as the assignments. Please check the course portal for those details and follow it accordingly. Thank you.